Let's begin class. So last time we were talking about the tangent plane, right? And the equation we had for the tangent plane. Maybe I should write a few of these things down just to remind ourselves. Because today I want to get into the directional derivative. And I have an activity for us to do that I think is I'm going to want to explore the directional derivative and try to come up with the formula. There's a nice formula. And if you've read the section, you've already seen it, but I think it falls naturally out of some considerations. And so, all right, so last time, tangent planes. Tangent plane to, we did it in the specific case. We're going to talk about tangent planes to level surfaces, basically functions given by an equation of 3 variables equals like a constant. But right now we're just talking about tangent planes to functions of 2 variables. At the point, I think we used a comma b, right? And we got the equation z minus, it's like z minus z naught is the x slope, which was the partial x times x minus a, plus the y slope, which was the partial y at that point, times y minus b. Just keep in mind that these are actual numbers, right? You're actually going to take a partial derivative and plug in a point and get an actual number. So, okay. And you know, the book probably adds the f of a comma b over to this side. But I think of this as just that point slope form where we know the point a comma b comma f of a comma b lives on the surface. And then these are the 2 slopes. And this really kind of came down to, because this is going to be useful later, is that this is really like a change in z equals f sub x times a change in x. Sometimes I won't write the of a comma b if I'm being a little bit lazy, times delta y, right? That's kind of where it came from. That was that picture we had of like the plane with the different triangles and parallelogram, and how the change in z was like another sum. This was like the change in z in the x direction, and this was the change in z in the y direction. And we saw that they added together, get the total change in z. And the reason I want to remind you of this is that I'd like to start going into directional derivatives, and it's going to be an important idea. So directional derivative. Oh, my R's and my V's look very similar. Okay. So I sort of mentioned that there's sort of a conceptual idea that if you're at a point on a surface and you zoom in, you basically start to see the tangent plane, just like we do single variable calculus. When we zoom in on a curve, we start to see the tangent line. And I want to sort of be at some point, here's my sort of tangent plane where I'm living, and I want to pick some direction to head off of, and then I want to know the slope in that direction. Right? We know the positive x direction, the slope is the partial x, and we know in the positive y direction, the slope is the partial y. But what if I want to head off in some weird direction? So the idea is, I guess there's the data that you need is, so given a function we'll almost immediately do an example, but at a point a comma b, what is the rate of change, the instantaneous rate of change slash slope in the direction given by, we're going to eventually make this a unit vector, but for sort of ease, for now, let's just say Let's just do a general vector. So we want to leave our point going in some direction. So as an example, let's think about something like f of x comma y is, I don't know, x squared plus xy at the point 3 comma 1. All right, let's make it 3 comma negative 1. Make it interesting. Okay. So let's pick a direction to leave this point. So we could write down the tangent plane at this point very easily now, right? But let's pick a direction. So like, let's just say the direction, like, I don't know, I'll draw this in a second. 1 comma 2. So let me just draw like an XY plane just to make it clear what we're doing. So here's, the top view. I'm not really looking at the surface yet, but we have the point 3 comma negative 1. So there's your point right there. And I want to leave that point. I want to leave that point in the direction 1 comma 2. So over 1 up 2. So it's going to be like that, right? I did that right. Point 3 comma negative 1. And I want to know the rate of change. What that really comes down to is following the tangent plane instead of following the surface, right? You could estimate the rate of change by just think about how you could estimate the rate of change. You could, actually, that's a good question. How could you estimate the rate of change? Like if I wanted to know, if I wanted an approximation for the rate of change at this point in that direction, what could I do? Just throw it at you guys. We definitely could find it. So that's actually getting towards like the instantaneous rate of change. But I'm talking about like the average rate of change, like how you would do it before. Like if I just want to guess like sort of the average rate of change. Yeah, you. Yeah, so right. So it's like there's a point here, which is the end of this vector. Right. I guess that's the point, what, 4 comma 1 maybe? So this is the point 4 comma 1, I think, if I go 1 over and 2 up from 3 comma negative 1. And so we could estimate the rate of change sort of more like the average rate of change. Or I guess we could just give the average. I mean, it's not really an estimate. We could compute the average rate of change from 3 comma negative 1 to 4 comma 1. So the rate of change of f from 3 comma negative 1 to 4 comma 1, right? It's just the change in the output over the change in the input, right? I mean, that's kind of what we do when we do rate estimate changes. But here, so Iman's saying the change in the output is really just plug in both these points to the function and take their difference, right? So that's equals to, yeah, the change in the output over the change in the input. Functions have inputs and outputs. And so here you're saying that's f of 4 comma 1 minus f of 3 comma negative 1. And then what about the change in input? Because we have 2 inputs, x and y. And I think you already said it. Like, what do you? The magnitude of, yeah, basically the length between the distance from these 2 points, right? Over the distance from 3 comma negative 1 to 4 comma 1. Or as Iman says, it's the same as the magnitude of the vector we wrote down, right? So it's worth noting that this is a change in z on top. And on the bottom, let me write it over on the left side here because I think I don't have enough room. We have a change in z on top. But we don't, normally you do like a change in x, you do like delta y over delta x, right? But here we have a change in x and y. Yeah.
So when it says like this, that includes the speed value or not?
Just in x and y. That's a good point. Just from these two-dimensional points. Or yeah, so I'll put in parentheses, this is also the magnitude of v. I guess this was v in this case, right? Okay, so that's worth noting that like it's not really the delta x or a delta y. I kind of almost want to put like delta xy, but I want to put like delta horizontal. Let me see if I can say this. So because in 3D space, vertical means z and horizontal means x and y, right? So that's the thing that's 3D vertical is the z direction and horizontal movement is x and y directions. Okay, so that's kind of a way to measure the average rate of change, or just like the rate of change. Okay, I don't even compute this because I want to think about the instantaneous rate of change, which gets back to the tangent plane, like you mentioned. So instead of following, if we want the instantaneous rate of change, I just want to say let's follow the tangent plane instead of following the surface. Does that make sense compared to like single variable calculus, where you follow the tangent line instead of following the curve? Okay, so yeah, for the derivative, for the instantaneous rate of change, which is going to be the derivative, which is really just really what the directional derivative is. Since we've picked a direction, follow the tangent plane instead of the surface. And now our delta z over delta horizontal okay, we could write down the tangent plane and plug in the 2 points, just like we did up there for the numerator to plug in the 2 points to the function. Or I have a formula for delta z right up there in blue on the board, right? And that's for the tangent plane. That's for following the tangent plane. So here it's the partial x times delta x plus the partial y times delta y over, well, how can we write down the magnitude of the vector? I'm doing sort of a general vector now. I guess I should say this is like, maybe I'm doing this in general and then I'll do it for the example. So this is in the direction it's kind of this vector, delta x comma delta y, right? Like that's the direction we're moving. We're changing, like there when I said the vector 1 comma 2, the delta x is 1 and then delta y is 2, right? So what's the magnitude of v? Yeah, it's just this, right? Delta x squared plus delta y squared. And so that's what we mean. We would be moving vertically along the tangent plane by this formula, and we'd be moving horizontally this amount, the length of the vector we're moving in that direction. Does that make sense? So let's compute that in this example. Okay, so this could be you could think of this as a formula for the directional derivative. It looks kind of unpleasant, but we'll get a nicer formula. But this for now, I mean, we'll get a sort of a more interesting conceptual formula hopefully by the end of class. But if we're just computing, like, let's follow the tangent plane and see the change in z along the tangent plane over the change in the horizontal movement, then this is what it is, okay? Okay, so in this example, maybe you should be computing ahead of me. So in this example, what's the partial x? Some good practice. Two x plus y, right? And the partial y, just x. Good. And so at the point 3, -1, that's what we want to think about, right? That's 2 times 3 minus 1, which is 5. And at the point 3, -1, this is just 3. So 5 and 3, the two numbers. Okay, and v is 1, 2, which is, so delta x is 1. And I could also write this as 1i plus 2j. So delta x is 1, delta y is 2. Okay, so then the directional derivative being lazy, 5 times 1 plus 3 times 2 over the square root of 1 squared plus 2 squared, is that right? So that's what, 11 over root 5, which may not mean that much to us, but hey, it's a number. It's a number, right? We found a slope. Hey, look at us. Our exciting question. Yeah, although it'll be in terms of unit vectors, but it's actually great. It's FU. Like instead of f sub x or f sub y, we're going to write, when we have a direction u unit vector, we'll write f sub u. So yeah, but since I'm not using the unit vector yet, I'll just kind of be vague. Okay, so that's, you can calculate that. Let's just pick a different direction just to see maybe something kind of interesting. What if we had, like, I don't know, let's try v is -3, -2 or something. So now leaving that point going in some sort of bottom left direction. So what do you get in this case? I guess it's just negative, right? You're basically putting -3 here, -2 here, and then you have to put these things here. So I think, yeah. So it's -21 over square root of 13. Again, these numbers may not mean a lot, but what's interesting, I wanted to do that just because notice, like, again, I want to think about the fact that when you're zooming in on this, like you're at this point, say, And this plane is tilted a certain amount and oriented a certain way. If I go certain directions, we're going up. But if I go other directions, we're going down, right? It's also worth noting there are directions where you can go horizontally and not go up or down at all, right? If I happen to go, I mean, just imagine yourself standing on a ramp, right? If you sort of go across the ramp, you're not moving up or down. There's also a direction you can go that goes up the fastest. So there's sort of a maximum rate of increase. This is kind of like the tilt of the plane, of the tangent plane. And there's a maximum negative rate of increase. It's in the opposite direction. Okay, so those are some first conceptual things. Here's what I want to do as an activity. I want us to compute a bunch of directional derivatives, and then I want to plot them. Because I claim there's a nice formula, like there's a nicer conceptual formula than this. I mean, this is the formula, but there's a way to reinterpret this formula. It's nice and conceptual. And it's like, what I want to think about is, how does this change as I change the angle? Like I kind of, or change the direction. And one way to measure the direction is like the angle, like an angle with, say, the positive x-axis, right? So for every vector v that you pick, you could compute, I want to plot the directional derivative versus some fixed angle, versus some angle, some reference point angle. So let me say it this way. And then I want to put it all in, all the data that you collect into Mathematica, and then I want us to plot it and look at it, because it reveals something interesting. My claim is it reveals something interesting. Okay, so activity. Let's just go ahead and use this function at this point. We might as well. Using x comma y, what was it? X squared plus xy. I mean, you already know the direction. You already know the partials. At the point 3 comma negative 1, pick a bunch of direction vectors v and compute the following. The angle that v makes with the positive x-axis, that's usually our reference angle, right? It's like that's 0 degrees is that way. Comma, the directional derivative in the direction v. So those are the two numbers I want you to know. I want you to give me those pairs. And of course, I just wrote that somewhere where the screen's going to cover it up. That was dumb. And I can't do the iPad thing where I just circle this and drag it over to here. Just sad. But I have a Mathematica notebook, which is basically an empty like place where we can type in data. And then a command to plot that data. And then I think there's something, we're going to see an interesting pattern is my plan. Okay. Yeah, it's really too bad. I was going to show you. Well, the Mathematica notebook I have is pretty blank. It's just like data and then it's an empty brackets because we don't have the data yet. But does this make sense? So why don't we do this? Why don't we break up into some groups? Do you want me to assign you to groups? Can you figure it out? No, you can't figure it out? Okay. Well, let me just kind of do it by area. So like, you know, maybe these two columns go to these boards, break up into some groups. And just basically compute some points, do some different directions. Try to get some different directions, not just always in the positive x, positive y direction. We want to go all the way. You're basically going to pick V's, right? So these two columns just break up into some groups, go to these boards. These two columns, the students can break up into some groups and go to those boards. Maybe you three can join them, and then you guys can break up into some groups, go to those boards. So just go break up into some groups, just a couple different groups, groups of like 3 or 4 people. And pick directions, just pick a V. You already know f sub x is 5, f sub y is 3. You have that formula. And then I'm gonna pull up. Oh, wait, somebody's here. And get the angle in degrees, it's just nicer. Sorry to be so maybe I should have put you guys in the groups more. Oh yeah, introduce yourselves to each other. Remember how group work works. Say hi to people, introduce yourselves. Learn names. I'm going to quiz you on each other's names. Oh. Yeah, you can use the stuff. Yeah, right. Yeah, that's just fine. Yeah. Yes, don't steal my job. Very important. So maybe you can record your points or your pairs like in the corner of a board where I can start seeing them and typing them in. Like once you have some of these pairs computed, start. Degrees is fine. Do you know how to find the angle of a vector? That's a question. I like it. That's how you find the angle. Yeah. Sorry, the angle of the positive x-axis. Okay. Yeah. I do want to say, if you give the angle, you should give it in between, angles in the 3rd and 4th quadrant should be negative or greater than 180 or negative, an angle in like the 3rd or 4th quadrant, a vector in the 3rd or 4th quadrant should have an angle that's like negative, like down is negative 90 degrees or 270 degrees. TD, that's a good abbreviation. If anybody's struggling with the angle, let me know. I see people getting there. Oh, and I do want the actual directional derivative as a number because I need to put data into the computer. So try to give me like a decimal approximation.
How do you want the angle?
I like over medium myself, but like you could do it from -180 to 180
Okay. Degrees.
degrees. Yeah. Hey, Lena.
I was just wondering if I could leave a little bit early because I have a meeting at 10.
At 10?
Yeah.
Yeah,
Okay.
that's fine. I don't want you to miss some of the good stuff. Here, let me write this between. Decimal point or something. Okay. Oh, I see some up there. So the directional derivatives I need as like a decimal number or something to input data. So if you can actually compute some of those numbers.
Or no, he says from 180 to -180.
But 0 is 5, 0 degrees is 5. Makes sense, actually. That's the F sub x, right?
And then for this one, we're gonna have 90 degrees. So that if you do trig, it'll get that angle, so you just do 90 degrees.
Wait, for 225 degrees, you got -50? For 225 degrees, you got -50? Oh, it's still -5. -5.0. Oh, wait, oh, 5.65, is that what that says? Oh, okay. Sorry. I actually have an eye doctor appointment next week, so I definitely need new glasses. -5.65? Okay. $26.565, comma, let's say 5.4. Or maybe my eyesight's not good enough. Maybe once you have some points, you can write them down and come up and we can put them in the data set. Or if you can see them from there, you can read them to me. That's a good idea. Take a photo. So I got your 26.565, 5.4. 0.87, comma,
Negative 0.6.
0.6. Okay.
Third one is negative 161.565. And negative 1.26.
2.6. Cool.
The last one is negative 75.964.
It's like the X, Y.
And negative 5.5.
Yeah.
5.578.
Then this
Awesome,
is the
thank you.
vector negative 7, negative 1. And
If you've computed a few points, you might also try to find the direction where the change is 0, or the direction with the biggest change. Stuff like that.
Or we could have done it as like this, I think, but it would have, we would have ended up getting this angle.
So I have a discrepancy between these two groups. You guys have 135 comma negative root 2. You have 135 comma negative 5.656.
Are you in radians? No. Oh, I am in radians. That would make sense. Okay, hold up. I'm gonna it's so weird. I know I did not use. I make do that. Yes, 81.9 degrees.
I sort of like your answer.
Makes a lot more sense.
I sort of like, because negative, you basically have the vector negative 1 comma 1, right? So you get negative 5 plus 3 on top. And that has length. Yeah. Okay, I think I like you. How did you get the negative 5.656? Oh, this is negative 135 degrees. Because it's down, it's pointing down to the left, right? Yeah, but you. Oh, sorry. Oh, but your partial x. Oh, the partial x and partial y are the same throughout the problem. So your delta x is negative 1 and your delta y is 1.
I wrote this. I wrote this wrong.
Right, but then in that case, your delta.
Because the partial.
No, you don't plug that point into the partials. The partial is only for the point.
Oh, so
3 comma 1.
Gotcha.
Yeah. Okay, again, if you have some points, come up and help me type them in because I can't see. So you had 135 comma negative root 2, negative 1.414. Can you read this? What did I got? Did I get your 225? Oh, I got your 225. And then 90 is 3. Yeah, that makes sense. .81. Oh, so that's interesting. So you were choosing nice angles, not nice vectors. 5.65. That's good. 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 Okay. Oh. Negative 0.45. Okay, awesome. Thank you. Like I said, if you've already given me some points, you can try to figure out the directions where the slope is 0 or where it's maximized. I need more points. I am hungry for more points. What does that say? 128.66, negative 0.781. hungry. Hold on. Wait, 128. Sorry. Caleb, what was that? 128 point?
Are we just doing,
Negative 0.781. Yeah, Sarah, what's up? Sorry.
are we just doing the magnitude of the angle that it makes or the direction?
Wait, an angle is a direction.
Like, is it just the value of the,
Of the angle, yeah.
but not just?
Not the magnitude of the V.
positive or-
Oh, I said between negative 180 and 180, because like you have 0 going this way is to 180, going this way is to negative 180. Do you have, oh, so those are pairs? Do you want to read me some of the ones you have?
90, that, and then negative, right?
So I'm getting 26.6 comma 5.81. Sorry, say it again.
Yeah.
Oh, for this direction, it's 26.6, 5.81. For this direction, it's,
90 plus that.
wait,
Wait,
no, 180 minus that.
yeah, because this is from that, yeah. I can't do that in my head.
143.1 maybe? $143.1? Is that right?
What'd you say?
143.1?
Yeah.
I'm a professional. And what was the directional derivative? Negative 2.2. All right, we're getting there. More points, anyone? Kim, give me your points. 74.74. 4.2. Nice. Can I bring the screen down now? Do you guys need to see this? I can't read that. Does that say? No. 5.09. Okay. With what? More points? Any more points? Oh, what's this over here?
The last one?
What's the one on the top right?
The degrees is negative 171.9 and the derivative is 5.37.
5.37?
Yeah.
Wait, negative 5.37. Okay, that makes more sense. Feels like it should be negative in that direction. Any more points? What about those groups in the back? Oh, yep. 127.87, comma 5.4. Really? Wait, 127. Wait, is it pointing? Is your vector pointing this way or this way? This way. Then the angle is not 127.87. It's pointing that way. So what's that angle? So I can't. I mean, probably some. Yeah, I don't think. 52.1. Okay. Any more points? Give me your points. Running out of time. Negative 71.5. Negative. Okay. Any more? Any more points? Nice. Are we good? Any more points? I feel like you guys haven't told me any points, right? These all accounted for. Okay. I don't care about the vector. I just care about the angle and the. $11.3. And then what's the directional derivative in that direction? 4.8. All right, maybe this is enough data. So you've given me a bunch of data. Let's hope you computed things correctly. And let's see what the data tells us. You ready? You ready? You ready for me to plot it? Okay, there's some weird stuff going on over here. There's some maybe inexact stuff going on over here. But, oh my God, some of these points are bad. What did you do? Oh wait, and some of these ones that are 300 and stuff should actually, I could do this. I could write 330 as negative 30, right? 300 is negative 60. Anything else that's above? Those might be. Oh. Okay, I really don't know. This point's weird. Which one is that? But it's only negative like 1 point something. Yeah, this doesn't feel right. All right, let's delete it. Bad point. This point also feels bad. Negative 80 something, negative 70, 80 something. Oh, up here? Yeah, that doesn't feel right, does it? Okay, so you might want to recheck those. Also, I don't know why these 2 points are a little bit off. This may just be a precision thing when you cut off after 1 digit or something. Okay, but do you, oh my God. Oh wait, I thought I got rid of that point. Oops. Didn't I? I thought I got rid of that point. Did I replot it? Oh, okay, thanks. Okay, so except there's a couple wonky points right here, but what does this look like? Yeah, I mean, we really need a lot more data, I guess. We should have done a little more systematically probably, but it looks like a sine curve or a cosine curve. Okay, and there is an angle. I mean, it's interesting to try to figure out the angles where the derivative is 0, because it's going to cross here at some point. And there's also a max value. What's the biggest value anybody got? 5.81. Is 5.81 the biggest value? There are 2 5.81s. Where's the other one? Oh, there. Oh, interesting. Oh, interesting. They're on opposite sides of something. So halfway between them, maybe. Yeah, so okay, so this looks like some sort of cosine graph, but it's shifted. I mean, it's shifted, but it's cosine, but we could figure out the direction of maximum increase. If we could figure that out, then we could sort of write this down as a cosine. I'll do this properly next time, but I want to sort of give you a little bit of a sense of why a cosine comes up here. The formula, the directional derivative formula, which is now partially covered. Direct deriv. We said is the partial x times delta x plus the partial y times delta y over square root of delta x squared plus delta y squared. What if we scale the direction to be length 1? Yeah, who's somebody who said that again? Yeah, go ahead. What'd you say? Yeah, the bottom becomes 1, right? Scale v to length 1. And then that just kind of goes away. And so you get that I'll use Sarah's notation, the DD is f sub x times delta x plus f sub y times delta y. What kind of thing does this look like? Anyone? The right-hand side of this looks like something. It is the delta z, you're absolutely right. But it's, there was the video about lines. I said we want to start sometimes to recognize expressions like this as dot product. This is a dot product. We could actually write this as the vector whose components are f sub x and f sub y times the vector whose components are delta x and delta y. But this is really our v, right? Or maybe call it u now. So this is this vector. The vector whose components are the partials dotted with u. This has a special name. It's called the gradient. The vector you make up out of the partials. So it's called the gradient of f. And it's written either grad f. I put an arrow over it because it's a vector, or there's also this upside down triangle notation. That's very common. Okay. And I just want to, just as the last thing, before we're out of time, if we write this, okay, if we write this in terms, so this is grad f dotted with u. This is actually the formula people use for the directional derivative. And I'll go over this on Friday, but what does the geometric definition of dot product say? Times the cosine. That's where the cosine comes from. This guy's 1. So another way to write down the directional derivative is the magnitude of this special vector called the gradient, which we'll talk about a lot on Friday, times the cosine of the angle that, oh my God, I'm on screen now, which is always bad. The cosine of the angle that you make with the gradient. And so I'll probably recapitulate this next time a little bit and for the specific example, but the gradient vector in this case was 5, 3. And that actually is about the right direction to have the angle, if you think about to have the maximum. If you just try to picture the direction of the vector 5, 3. But I'll go through this all more carefully because we're out of time. But all right, but that's the exciting thing, is that's where the cosine comes from. You can plot the data and see it's a cosine, and it really is a cosine. Okay. Thanks, everyone. Oh, and I need to I'll post the Friday problem set